Mr. President, ladies and gentlemen, it's a great honour for me to be invited to give this memorial lecture, and I do so with great pleasure. The topic which I have chosen to speak about may seem a little strange at first, because we have trained ourselves not to ask the kind of question which I am asking. For example, I might have brought with me some of the simple models that we construct to represent a molecule. You see, I could have represented the water molecule by one solid sphere here and two strings of some sort, and then two hydrogen atoms there. And I could have represented the methane molecule by a carbon there, and then, of course, four hydrogens in the tetrahedral directions. And if I brought those models and we looked at them, you would have seen that exactly the same little sphere represented the hydrogen in water as in methane. In fact, if we use those models, which we do, we don't allow the possibility that the atom will be altered by being part of a molecule. And it's really that kind of situation to which I'm going to address myself now. What does happen to an atom when it becomes part of a molecule? This is not now quite such a theoretical problem as it would have been even only a few years ago. One of the, to me, interesting features of the situation at this moment is that recent experimental developments have been able to confirm quite a few of the theoretical predictions which were made in earlier years, and there's now a most interesting interplay of theory and experiment which make it possible to tell the story which I'm going to be telling for the next 45 or so minutes. It might conceivably help us if I were to put on this left-hand board the agenda for this lecture. It comes in four parts. The first question that I shall consider is simply that of size. Does an atom get bigger or smaller when it forms part of a molecule? The second question that we'll deal with is a change in shape, which I shall represent by simply writing deformation. Now, those two paragraphs deal with the atom as a whole within the molecule as a whole. But since we all know perfectly well that what we're talking about is the behavior of electrons, we might then say, well, what happens to individual electrons? And then when we've done all that, what we might call a little fun at the end, an apparently foolish question: where is the nucleus? Well, there we are. That's what we've got to talk about. Let's begin with the first of them. What happens in the way of size when an atom gets into a molecule? Now, first of all, what kind of description are we going to give for this sort of situation? Atoms aren't these little billiard balls with holes in which we use to build models. They are a nucleus surrounded by a series of electrons. And we think of those electrons most profitably for our present purposes in terms of a cloud. So that I want you to have in mind, if it's an atom we're talking about, the nucleus here, and then round it a whole cloud of what is negative electricity, the total amount equal to the number of electrons which are involved. And we shall talk about the density of that cloud. Where the density is high, that means that more of the electronic charge is to be found. Where the density is low, less. That density has to be calculated by using the Schrödinger wave equation. I shan't go into the details of that one tiny scrap, though behind what I'm saying there does lie quite a lot of calculation, as some of you know very well. But I'm going to speak about the results, so that we shall be concerned then with understanding the varying density at different positions in an atom or a molecule. How should we represent this density in the most satisfactory way? And the answer there is, without any doubt, by using contours. If we take the first slide, which we shall come back to again after a moment or two, we can see what I mean. These are some contours of charge density at different positions in the simplest of all molecules, the hydrogen molecule. And you can see the one nucleus here and the other nucleus B on the right-hand side. At all points which lie on one of these contours, let's take this one, the density has the same value, and you can see that the numbers get smaller as we go away, so that the density is decaying, the cloud is becoming thinner and thinner, and in fact this outer contour which I've drawn here represents effectively the kind of boundary of the hydrogen molecule. And you can see now how, in a certain sense, there is one hydrogen atom on the left and the other hydrogen atom on the right. But there are changes, and of course it is those changes which we're now going to think about. And the first of them is the matter of size. Now here I've got to divide my agenda into two parts, because when an atom forms part of a bond, it might be a covalent bond, or a largely covalent bond, or it might be an ionic or polar bond. Let's take the covalent one first. The situation here is now very well established. If you take an atom and put it into a molecule and there are no large migrations of charge, then the atom contracts. And there's a very simple explanation of that, which is now a classical model, but it goes over into quantum theory. Let me suppose that I have got the hydrogen molecule like the thing on the right. Then I've got a nuclear charge plus E at the two positions here, and first of all, one electron, shall I say, at the point P, charge minus E. That electron is being attracted to this nucleus with a force along that line. It's being attracted to this nucleus with a force along that line. And the net force on it is the combination of those two. Now, quite obviously, the combination of those two will normally be bigger than either of them alone. So that we may say that the electron, when it is at that point P, is being pulled towards, if you like, at first, this nucleus with a force which is bigger than you would have if we could obliterate this right-hand nucleus. So it's pulled in. Well, if it's pulled in, then naturally enough you expect the cloud to shrink. That's exactly what happens. There's confirmation of that now. This is the first of the examples that I'm going to take in which we find that theory and experiment are agreeing. Let me, first of all, take the theoretical side. However, before I come to the details of it, let me dispose of a possible objection. You may say to me, but the hydrogen molecule has got two electrons. And so when I put the next one, which I'll call Q, onto this diagram, that will push the first one away. And won't you undo by that means all the good you achieve by having it attracted simultaneously to both nuclei? The answer is no, because if I put the second electron there, it's quite true that that second electron does repel the first, but by this one getting on this side out of the way of the first one, you do in fact not cancel the extra attraction, so that this is still pulled in a bit further. And what I'm talking about in that simple model is what, in a much more sophisticated way, people calculate under the heading of correlation of electrons. So, if that be so, let us look at the matter and mention the results of some very simple calculations. if I have an isolated hydrogen atom at that point, then the charge density that I'm talking about varies with distance r from the nucleus in the following way. It's proportional to e to the minus 2r. I'm choosing appropriate units of length, but that doesn't affect my discussion. It means, of course, that as this is an exponential function, as I go away from the nucleus, the charge cloud drops down exponentially. Well, now when I put this atom into a molecule, and I have two different centers, I can still build up a wave function using the same kinds of functions as were used for this one, but now the density goes in the following form, e to the minus 2 zeta r, where I've introduced a coefficient zeta, which is equal to 1 here for the isolated atom, and turns out to be about equal to 1.2 for the atom in the molecule. And therefore, when we're in the molecule, I've got to draw this graph instead of that graph. And it's not difficult to see that the second graph comes on the inside of the first one. So if you like, that's the situation in the atom, that's the situation in the molecule. And it means that the charge cloud has dropped to a very low density here, while it's still appreciable for the atom. The whole thing's contracted inwards. Now, that's been well established by calculations, so there's no doubt about it. But what about the experiments? Well, some years ago, Professor Coulson in Edinburgh made some extremely careful X-ray measurements of the scattering of electrons from a variety of crystals. One of these crystals, whose details don't concern us now, involved a hydrogen atom. So that here was a situation in which, if the experiments could be done accurately enough, one might be able to get some kind of test of the theoretical prediction there. Well, the experimental conditions are difficult. I'll say a word about that perhaps later. You need extremely good measuring apparatus. But what he found could be put in the following way. Let me suppose that that is the center, the nucleus, of the hydrogen atom whose charge cloud density he was determining by experiment. He said, let me consider how much of the electronic charge would lie within a sphere. He took a sphere whose radius was 1.1 angstroms, and when he did that, he found that 0.92, 92 hundredths of an electron was to be found within that sphere. Most of it, because after all, with a hydrogen atom, we only got one, so this was indeed accounting for most of it, and most of it was within that sphere. But it's very easy to see what the situation would have been if, instead of the atom being part of the molecule, it had been all on its own. Because here is a problem for which we have got absolutely clear-cut experimental and theoretical work. And the answer would have been 0.84 E. So that here, 16 hundredths of the electron would have been outside that for the atom, but in fact only 8 hundredths is outside when the atom is part of the molecule. So it's sucked charge in. Now I know that these figures are terribly hard to get right, but curiously enough, if you make use of this wave function with zeta given that value, what you would predict would be actually precisely 0.92, correct to 1%. So that, somewhat fortuitously probably, the agreement between experiment and theory is perfect for this, and I think we can reasonably say that when you have a covalent bond joining two atoms, the size of the atoms is reduced. But what about the case in which the bond is a polar bond. Here, we shall not expect to get the same situation at all. And we can see that quite easily if I consider an atom, and for the moment, let's keep it all on its own. It has associated with it a certain number of electrons, and let me suppose that they occupy a charged cloud represented somewhat schematically in that way. Well, now let me add to this one more electron. Of course, in most chemical bonds, I don't add one electron, but I might well add up to half an electron if it's a polar bond, like, for example, HF. Well, let me add then one electron, and then instead of having, shall I say, n electrons, I've got n plus 1. Now, these are always elbowing one another out. They repel each other. And when there are n plus 1 of them, there are more forces pushing them out than there were before. In fact, a great many more, because it's the number of pairs that matters. And the result is that then they're pushed out a bit, and so the cloud would go out some further distance. So here's something that we would expect. If we have too many electrons around a nucleus, the atom will swell. Conversely, if I took an electron away, there would be fewer electrons, and they would all be sucked in more by the nuclear attraction. In other words, we expect that there will be a relation between the number of electrons, if you like, the deficit or the excess compared with the neutral atom, and the size. Now, that can be illustrated by some very pleasant calculations, which I'm now going to show you. I think at this stage we should turn to the next of the slides. This slide represents the contours for a series of molecules, all hydrides. This one on the top is lithium hydride. And then you go around beryllium, boron, carbon, nitrogen, oxygen, and fluorine. So that you've got a motion right across the periodic table from left to right. Now, these are drawn in such a way that hydrogen is always on the right. But in fact, I think the top one has somehow got inverted. It has. Let's worry about that one. I've got another example which will show exactly the same thing in a moment. When you go across the row of the periodic table, you know that the electronegativity of the element increases, so that lithium is not very electronegative, it's electropositive, and by the time you've got to fluorine, it's very electronegative. So that you would expect, as you go across that row of the periodic table, that the hydrogen atom would, to begin with, in lithium hydride, have more than one electron. You know that from electrolysis experiments. But by the time you've got to the end here, the fluorine will have sucked off so much of the electron that very little will be left. Therefore, at the beginning of the table, the hydrogen atom should be big. At the end of the table, it should be small. And this is exactly what is shown, missing out that top beggar up there. Here's a hydrogen atom, which is really quite big. It's getting smaller, smaller, and so on, until by the time you've got to HF, the hydrogen atom is like a little pimple on the skin of the fluoride ion. Now, those are calculations, because at the moment there aren't corresponding experiments. But the sophistication of calculations today is such that there's very little doubt about the general pattern which those diagrams show. Let's take the next slide, which brings in lithium again. This is another diatomic system. Now, you won't, if you're a chemist, expect to find bottles full of diatomic lithium fluoride. After all, lithium fluoride is more important as a prism for spectroscopic work than it is as a diatomic gas. But there are some circumstances in which you can get it, and it illustrates my point at the moment. That's why I've chosen it. Yeah, if someone were to say to you, what is the difference in size between a lithium and a fluorine atom, your instinctive reply ought to be, of course I don't know what it would be, but it ought to be, oh, a lithium atom is immense. It's only got 3 electrons. 2 of them are in the inner shell, the K shell, and then the outer one is in an immense orbit called the 2s orbit. Not very tightly bound, that's of course why it's an electropositive element, and very large. Fluorine is very small. 2/3 of the chemistry of fluorine is embedded in that single statement. Fluorine is a very tiny atom, much smaller than lithium. Well, here's diatomic lithium fluoride. Which would you think was the lithium and which would you think was the fluorine? Well, if you didn't think, you would say, oh, obviously, that's the fluorine and that's the lithium. But of course, you would be wrong. When you did think, you would say, oh, but lithium fluoride is a very polar bond. That means that the lithium atom has given up practically all its outer electron, and what's left is the inner pair, the K shell, very small. And the fluorine has got an extra electron to make the fluoride F-, and that becomes very big. And so this is lithium fluoride. And it well illustrates the danger that there is in using some of the tables of atomic diameters, radii of atoms, which you find in textbooks. In a sense, I'm warning you against some of the things which you will find from time to time in the textbooks. So we now reach a situation where we can say that a bond which is covalent leads to a decrease in size of the atoms. If it's polar, then it leads either to an increase or a decrease, depending on whether charge comes or goes. And I'm going to put a tick against the first paragraph and say that though there's more, of course, that could be said about it, that is the bones of the matter. What about the deformation? Well, let's go back to the very first slide that we had. Here's the hydrogen molecule again. I said when I first mentioned it, oh, well, here's the one hydrogen, here's the other. But you could perfectly well have said, well, they look a bit distorted from what they would be if I only had one atom at a time, and I had perfectly spherical contours. And they look distorted because, quite apart from anything else, here we've got a kind of build-up, a plateau of charge as compared with the corresponding positions on the far side of the nucleus. If this was a contour map and you were doing some mountaineering, you'd say here is one peak, and here is another peak at the 2 nuclei, and here is a little plateau in the saddle between the 2 peaks. Now, the existence of that plateau means that these atoms are not anymore spherical. So there's another little mistake we make when we take those wooden spheres and join them together, because that makes them spherical all the time. They're not. And we want to study now this lack of spherical character. The reason why we get that can be seen if we can turn for a moment to a diagram which I did have on the board. We can look at it again. You remember how I said that if you have an electron here being attracted to those 2 nuclei, then there are 2 forces represented by those arrows, and of course the resultant force would then be represented by a bigger arrow in that sort of direction. But not only is that force bigger than either of them, compressing the molecule, but it also directed more strongly towards this sort of area, this being one nucleus and that being the other. This is the area, or volume more properly, to which the electron is being pulled. So you would expect to find an increase in charge density in this region. That region is generally referred to as the overlap region, because if I start with one atom, and then if it's a hydrogen atom, represent its charge cloud in terms of a little kind of sphere, and then if I take the second one and its sphere of charge, the region where those two spheres overlap is the region I've shaded, and that is precisely where this build-up occurs. In fact, when you look at it mathematically, it's because these two separate diagrams do overlap that you actually get the bond formed at all. And the strength of the bond is related to the amount of overlap, as we'll see in half a moment. But the fact that you do have this build-up here means that you have lost charge from somewhere else in order that it may go there. Now, that is shown us on our next slide. This is an old slide representing the density in the hydrogen molecule along the axis. So here are the two nuclei and the axial line. And you notice the two peaks, as I was calling them, in terms of the contour diagram at A and B. And here is what I call the plateau. And you see how much bigger it is here than it would be even if you took twice the amount at a corresponding position on the other side of the nucleus. So now if I had an isolated atom, I should be up above this curve on the left there, and then of course I should come down below it on the right. And the existence of the bond has meant that the atom has been, as it were, deformed, and deformed in the direction in which the bond is to be formed. That's perfectly general. Let's look at the next slide. Now, perhaps this is still on hydrogen, but it shows the deformation very well indeed. It's a diagram which the crystallographers now are very fond of, called the difference density. It's a difference. You take the density that you get at any point of space in the molecule, and then you take away from it what you would have if the two atoms were just slapped down on top of the nuclear positions without any interaction whatever. And then what the difference between those represents the effect of forming a bond. Since you're dealing with the same total number of electrons, whether the atoms interact or not, this means that the total amount in the difference density must be zero. It'll be positive in some regions of space, negative in others. In the positive parts of space, making the bond has built up charge. In the negative ones, it's taken away. And so here, for the hydrogen molecule, you've taken away from the far left and the far right, and you've concentrated really into the middle here. Where you have a solid line, a difference density map always means an increase in electron density as a result of the bond. Where you have dotted lines, a decrease. We'll have some more diagrams later in the same convention. Well, that's for hydrogen. Now let's go to the next slide. This is the total density for another rather unusual chemical species, diatomic lithium. I've chosen this simply because we've already been talking about lithium, and good calculations can be made. Unfortunately, there are no experimental results that are adequate for this purpose yet. You can see in the diatomic lithium case how around the one nucleus you've obviously got two electrons, and they are the inner shell that I spoke about, and then of course another two around this other nucleus. And what's left are the two electrons that constitute the bond. And they are represented in effect by all this other charge contour system. And if we could, as it were, superpose this one and the very first slide I showed you, you'd recognize how similar they were. That you've got very much the same situation in diatomic lithium for the bond as you have in diatomic hydrogen. You can see this if we take the next slide, which is the difference density. Here's a nucleus around here, and here's the other nucleus around here, and here is the build-up where you've got solid lines, and here is the decrease where you've got dotted lines. Don't worry about that little bit of solid line. That may or may not be genuine. The calculations, I don't think, guarantee that that's right. But it wouldn't much matter even if it were. It's only a very small part of the total. Basically, the same situation, the atom is being distorted to give a positive increase of charge density in that direction, and on the whole a negative one in the other direction. And there is the build-up in the middle. Now the next slide shows a series of these for other molecules. This is the lithium-2 one we were looking at a moment ago. It differs in that a lot of the contours in this little inner region have been missed out for simplicity. Here's diatomic boron, diatomic carbon, nitrogen, oxygen, and fluorine. And in every case, you can see a little plateau. Here we are in diatomic fluorine. Here you've got it in diatomic carbon, and so on. So that in every case there, as a result of forming a molecule, the atom has been distorted in the direction in which the bond is to be formed. That is now completely well established, and what's more, there is at last experimental verification for it. You may wonder that I put my last sentence in the way I have when I spoke of at last. And this is a moment to say something about the kind of accuracy which is needed if you're going to do the sorts of job that we want today. When there is a build-up, as we've got in the middle between the nuclei, in cases like those on the slide, how much charge are we dealing with? The answer is that we're dealing on the whole with something between 1/10 and 1/4 of an electron. Now, that isn't very much. Let's suppose that we're taking methane. In methane, there are 10 electrons. You're trying to find what might be only 1% of that total. You've got to do your experiments very well before the answer that you get is very meaningful. And that is precisely why it's taken something like 30 years since the predictions about this were first made to the time when really adequate experimental confirmation has been available. But it is now. And I'm just going to mention one example, then we'll have a few slides to show some others. Oddly enough, the most satisfying of the examples until just a year or so ago was that of a what I'll call a molecule, if I may, a diamond crystal. Now, that's an odd molecule, of course. It's a very big one. If we've got one carbon atom here, then we know it's surrounded by 4 others in tetrahedral directions. And then this one is surrounded by 4 others, of which, of course, that is one. And then those are the others. And a fairly good description of diamond is to say that we have got a series of bonds joining adjacent carbon atoms, and each bond is due to 2 electrons, and the charge distribution for those 2 is similar to the situation that I've described, say, for hydrogen. That's not quite a correct description, but it's not far wrong. Now, the advantage of diamond is that being a large crystal, you can make reasonably good X-ray measurements tolerably easily. And let me give you just one pair of figures to show what I mean. Let us compare the density of electronic charge at that point, which is midway between 2 nuclei, in fact in the center of one of these bonds, with the density at a corresponding position there on the other side. Now, bearing in mind the tetrahedral character around this carbon, if that direction is along one of the bonds, this is between 3 of them. So that if my model is correct, we should get a bigger density at the right-hand position in the bond than at the corresponding left-hand position between bonds. Of course, if the atom was spherical, we should have the same, shouldn't we? Well, the values in appropriate units at the center, 1.59, and midway here, 0.72. Now, that shows extremely clearly, experimentally, the situation that I have been describing. But there are some other very interesting applications of this, and one of the most pleasant is shown in the next slide. I'm going to talk for a few moments about cyclopropane. Now, this is an old friend of mine. I've been on reasonably good terms with cyclopropane now for about 30 years. He's still got something to tell us, but as you all know, it consists of 3 carbon atoms at the corners of an equilateral triangle, and attached to each carbon atom are 2 hydrogens. Now, I can't represent them satisfactorily. If you take the carbon I'm pointing to, the 2 hydrogens lie in the direction, in a plane that goes this way, towards you, one above and one below the plane, so that you get roughly tetrahedral directions at the carbon atom here. Well, I'm not concerned about the hydrogens. I am concerned about the lines or the bonds joining the carbon atoms. If the bonds could be straight, I'm going to say what I mean by this in a minute, if they could be straight so that from here you had a bond going straight across to the other carbon atom over there, then at each of the carbon atoms you would have 2 bonds, one there I've just done, the other one going up there, and the angle between them would be 60 degrees. Now, it was one of the very early discoveries that you couldn't get bonds from carbon that went straight at 60 degrees. You couldn't get anything less than 90 without doing the most unnatural things which no one believed that one would do. Now, what do I mean by straight and bent? Here is a straight bond, the sort of thing you would get in ethane, where there's nothing to prevent the electron density for the 2 electrons that make the carbon-carbon bond from being along axially symmetrical around the line joining the nuclei. The overlap region is here, so the build-up of charge is there. Now, if you can't do that, you have to do something which is symbolically represented here on the right. And you must excuse me if I don't go into the details of this, we haven't time. But you start off with an atom which is polarized or distorted in the direction of that arrow, and the other one in the direction of that arrow, and then you make a charged cloud which is bent. In fact, you could think of it almost as if it followed a kind of arc of a circle from one nucleus to the other. In a frivolous moment, we call these banana bonds. But whatever language we use, there's clearly a difference between this and this, because the build-up is here, midway between the nuclei. The build-up here is at this point I'm putting my arrow to my stick towards way off the center. Well, that prediction was really made on the basis of calculations which were completed by Bill Moffat when he was a student reading for his doctor's degree in Oxford just immediately after the war. And they remained a prediction until quite recently. Now, the next slide shows a molecule, not exactly cyclopropane, but a derivative in which you've got the 3 carbon atoms here, 1, 2, 3, in the equilateral triangle, and you've got 3 hydrogen atoms here, here, and where's the other one? There, below the plane. But instead of 3 above, you've actually got cyano groups. You see, C, N. Now, the reasons for choosing that were technical ones. It was much easier to study that molecule with X-ray diffraction. Now, it's fairly obvious that what happens out here, way up above the plane, is not going to make much difference to what happens in the plane. So let me show you on the next slide the difference density map for this particular tricyano cyclopropane molecule. And you see that if these are the positions of the carbon atoms, you have got build-up, solid line, build-up of charge. You've got 3 places of build-up, but mercifully, they're not on the line joining the nuclei. They're just where I said they ought to be on the basis of bent bonds. So here is really a very lovely verification, not just of the idea of a build-up, a distortion of the atom, but also of the picture of bent bonds, which of course has now become part of the vocabulary of the organic chemist. And I regard that as one of the most lovely illustrations of the agreement which you can get between theory and experiment when you go about it in the right way. There's another example which we'll turn to now before we leave this. And this comes on the next slide. This is a molecule of interest to some organic chemists. S-triazine. Triazine is a planar molecule, rather like benzene, with alternate atoms, nitrogen, then carbon, then nitrogen, carbon, so on, round the ring, and then sticking out from the carbons are hydrogen atoms. So its formula would be C3H3N3. Now here is the difference density for S-triazine. And I want you to notice two parts of it. First of all, on the line joining two atoms in the ring, that would be nitrogen and this would be carbon, there is a build-up with solid lines. It isn't quite central. I don't know why it isn't. I suspect it may possibly be difficulty in making allowance for the vibrational motion. But that doesn't matter. It obviously is the build-up that we're used to along the line of centers. But here, outside the nitrogen, nitrogen there, outside here, is a substantial build-up of charge. What the dickens is that doing? What's a nitrogen atom doing, pushing charge out there? Now, it's really an extremely interesting position that I'm going to describe. I won't deal with that molecule, it's unnecessarily complicated. But I'll deal with a very much simpler one, ammonia. In the ammonia molecule, you have two electrons which make a bond there, two more which make the other bond and the other bond. And if you then go into the situation around the nitrogen atom, you find there are two electrons left. And when you study the precise way in which those electrons have to be distributed, you discover that because this bond has deformed the atom this way and that one and the other one in that way, what is left must go that way. And so what we call the lone pair electrons, I want to send that up a little bit further. No, that's not. No. Let's see. Blue one, I want to go up. Now we don't lose the shadow. Now, the lone pair electrons center themselves in a volume up there. In fact, they give rise to the characteristic behavior of ammonia. Why, it's basic. You can add a proton here. The two electrons are just sitting pretty, waiting for a positive charge to come and be gobbled up. So that it's very rational chemically, but it also turns out to be correct in other respects as well. Those electrons are the ones which I drew your attention to out here. So that was, I believe, the first really clear demonstration of what lone pairs around the nitrogen atom would look like. Well, very briefly now, we can rub off, or tick off, this. Now, we understand something about the deformation of the atom. Now, what about the behavior of individual electrons? We're talking now not so much about the totality of all the electrons, which is what you're discussing over there, but individual ones. An electron starts off in one atom. The other atoms come up. What happens to it? Well, of course, it has to be thought of now as no longer localized on one nucleus, but spreading itself. And how do we discuss this spreading? Well, there's a whole language which has been devised for this, and as soon as I begin to talk about it, some of you will recognize why I'm saying what I am about it. Now, the first feature in that language is that we talk about hybrids. Hybrids, for example, of S and of P. An S-type orbital for an atom is spherically symmetrical. I could represent it like that. A P-type is rather like a dumbbell. But if I take a combination of those, for example, S plus lambda P, where lambda is some constant, then I get something like this. Now, this would be very much more suited to overlapping with something. Shall I bring a hydrogen up? Put it there. much more suited to overlapping with a hydrogen than this or that would be, because in rather anthropomorphic terms, you waste such a lot of the cloud there, you can't use that half at all. Whereas here, you're wasting much less. Well, that's one rather crude way of talking. What I'm really claiming is that when you make a bond, the electrons no longer are in atomic S or P or D, but in hybrids or mixtures of these. This was studied most carefully first by Pauling and then by Slater, but Alan McColl of University College, London, produced a diagram which I've transcribed substantially in the next slide. Here is what he's called the percentage of S character in a mixture. So that would be a pure P having no S. This would be a pure S having 100% S. And here is an overlap integral. That is a measure of the way in which an orbital of that sort, a mixture, a hybrid, can overlap with another similar one, two carbon atoms, say. And you notice how this curve goes up and up and up, and when you have equal amounts of S and P, as you do in acetylene, you've got a maximum. When you have this, as you would have, say, in ethylene, you've got slightly less. Here is the saturated carbon atom, the paraffins, slightly less, but obviously far better than either extreme. Well, that shows that when you're describing a bond, you may bring in electrons now and think of them in this kind of hybrid. Now, the next slide shows how that affects the size of the atom. Because if you have equal amounts of S and P, the covalent radius shown here is less than if you have the ethylenic or aromatic carbon, and less still than if you have the saturated carbon atom. So that you have a little bonus thrown in when you start talking about hybrids, in that they give you some information about the size of the atom. And now that is the kind of language which we use. But that applies just in the neighborhood of one nucleus. What sort of picture do we have for a more elaborate system? Well, let's take an example. We're going to take the carbon monoxide molecule and see how it is made up out of parts. The next slide gets us started on this. Here is the contour diagram for carbon monoxide, the carbon and then the oxygen over here. And well, we're used to that sort of diagram. You don't get very wildly excited when you see it. But what I want to do is to show how that is composed of parts. There are 10 valence electrons in carbon monoxide. So that if we adopt the molecular orbital description, they will go in pairs into 5 molecular orbitals. These individual molecular orbitals will be made up out of hybrids. Well, I'm not going to discuss that part of it because we've seen that. But let's just see what these different molecular orbitals look like. The ones which are added together in giving this diagram. Now, we'll go quite quickly through them because the details aren't going to concern us. The next slide. Thank you. Here is the most strongly bonding. You can see the oxygen here and the carbon at the other end, and most of the cloud is between the nuclei. So that would be a very strongly bonding electron. The next one, please. Here is carbon here, oxygen here. Here are electrons on the far side of the oxygen. They're the things chemists call lone pairs on the oxygen. 2 of them. Next one, please. Here's another one. Here's the carbon. There's the oxygen. So most of the electron is out here. These are really the exciting electrons in carbon monoxide. I can spend a whole hour talking about those 2 electrons. They give carbon monoxide its properties. That's why you get the transition metal complexes with the carbonyls. They use these electrons primarily to attach themselves. Well, you've got 2 of those. Now the next one. Here's rather a different sort, a pi sort instead of a sigma sort. The oxygen here and the carbon on the right. Most of it around the oxygen, but a bit pulled away towards the carbon. Now, add up all those and you get my first slide. But we've now got a lot more information. This molecular orbital description is telling us quite a lot that we didn't know if we only saw the total density. And this was the position which was really produced by the work of Robert Mulliken in Chicago. He made the predictions and the rough calculations a long time ago. But it's only just recently that there has been adequate experimental confirmation of this. I brought one example, which in fact I begged from W.C. Price in King's College, London, to illustrate what I want to. The example is that of diatomic nitrogen. On the left of this diagram are what the theoretical chemist draws for the energy diagram in diatomic nitrogen. These are inner shell electrons. We won't worry about them for the moment. In the valence shell, you've got 1, 2, then a doubly degenerate one, and a final top one. And the picture which we have from molecular orbital theory is of electrons, 2 at a time, in the orbitals which are shaded with the arrows. And that lacked any really significant confirmation until the advent of photoelectron spectroscopy only 6 or 7 years ago. In photoelectron spectroscopy, in the form in which I am thinking of it now, you shine a beam of radiation of well-defined energy, normally comes from a helium atom or a helium ion, and that energy is enough to kick out one of the valence electrons. Now, if that valence electron is tightly bound, there won't be much left over, and so the electron which is kicked out has a slow velocity. If the electron is not very tightly bound, well, then it doesn't need as much energy and it's kicked out faster. And by measuring the distribution of speeds or energies of the electrons kicked out, you can work back to a diagram of this sort. Well, this is what you actually get. It's on the right-hand side. And here, this one, referred to here, this one referred to as sigma G2s, most tightly bound, is here, binding at about 32 electron volts. Here's the sigma U2s, the next one. Here's the doubly degenerate one here. And here's the top occupied one. Now, I could have brought diagrams which would do much the same thing for many other molecules, and really one almost begins to feel that one can see a molecular orbital after you've seen a few diagrams like that. Theory and experiment really gearing themselves in very nicely. So we begin to know quite a lot about the individual electrons, but there's still a bit more that we can find out. I've been talking there about the valence electrons, but I could have talked about the inner shell electrons. And here another experimental technique has come in the last few years. Now, I'm going to put this on the board for a moment because we speak nowadays almost entirely in initials, and so I am referring to S.Car. As it was originally designed by Siegbahn in Uppsala, that stood for electron spectroscopy for chemical analysis. And in fact, it is the best form of chemical analysis in many purposes. However, it does more than analysis, and so it's been rechristened electron spectroscopy for chemical applications. There are certain advantages in using only initials. Well, the next slide will get us onto this. Here is, on the top, the sodium azide molecule, NaN3. Now, we know perfectly well that the sodium atom gives up its electron, particularly if this is in solid form, and the N3 group, therefore, becomes N3 minus. And for a long time, people have drawn it, bond diagram, as I've got it here, with 2 double bonds. But that's only possible if the central nitrogen is positively charged and the N nitrogens are negatively charged. Otherwise, you don't satisfy the valence rules. And people have believed that. But what was the evidence for it? The answer was practically none, until quite recently. What these people do with S.Car is to use a very much more powerful beam of X-rays, this time, of high energy. High enough energy to knock out not a valence electron, but an inner electron, very tightly bound. And so in this case, they would knock an electron out of that nitrogen atom or out of that nitrogen atom. And there is a difference between the two, which is most interestingly related to the charge on the nitrogen atom. Let's suppose there are a lot of electrons around a particular nitrogen atom. It's N minus. Then, since electrons push each other about, if an electron begins to go, it gets pushed by the others much more strongly than if you'd had a neutral nitrogen, and even more strongly than if you'd had a positive nitrogen. So the ionization potential of an inner electron in N minus is much smaller than in N plus. Well, what they measure is in effect that, because they measure the speed with which the electron is kicked out. And this is what you get. 2 peaks, that's wonderful, 2 types of nitrogen. This one twice as big as that, so we know which is which. This refers to the N nitrogens, this refers to the middle one. And then look to see what the binding is. The binding energy in the middle one is bigger than in the end ones. This bottom slide goes from right to left in the scale. So that shows that this diagram is correct. It is N minus, N plus, N minus. That's rather nice that we begin to see that much about an atom in a molecule. Even the same type of atom being different. How foolish to take one sphere and call it nitrogen, whatever happens. Well, now let's go on, because there's more. Next slide. We can go quite quickly at this stage. Here is a group of results in which people have calculated the charge on the nitrogen atom, and here they plotted experimentally the binding energy. And you see a whole horde of experiments all fit nicely on a curve, except for those 2, and there are particular reasons for those, but we haven't time for that now. So this is a good way of saying just what the charge will be in a given molecule containing a nitrogen atom. Here is a case of carbon. It's a very familiar one. Perhaps one shouldn't show this now, but if you haven't seen it, it's great fun. Here is the molecule, and it's got 1, 2, 3, 4 carbon atoms. But they're all in different environments. This one has got 3 electronegative fluorine atoms around it, sucking electrons away like blazes. This one has got 2 electronegative ones, 2 oxygens. This one has only got 1, and that's got none. So that we would expect that this would be more like C+, and you would go along until you got to C neutral here. That means that if you used the SCAR method and kicked electrons out of the inner shell of the carbon atoms, you ought to get 4 different peaks. Well, you do. There they are. And what is rather pleasant, and this is why I like this slide, is that each peak points to the carbon atom which it refers to. If you look at the bottom, the greatest binding energy comes with the left-hand one, and that's the one which has been deprived of most of its electrons and is more like C+. Well, it's rather nice. They're all the same. Let's go to the next slide. Here is a whole set for sulfur in different situations. And it shows that what applies to nitrogen applies also to sulfur. Shall we look at the next slide now? That's the next thing I come to just before we finish. What I want to do now is to put a tick there and turn to the light relief. But the light relief is in the form of a question. Where is the nucleus? Well, we've been talking about bond distances all the time. Why do I now say, where is the nucleus? And the reason is really very interesting, and again the result of improved experimental techniques. When you're using X-ray scattering, what you're finding is the electron density. X-rays are scattered by electrons. So that when the X-ray crystallographer gives you his results, he gives you the distribution, the density, if you like, of the electron charge. He says nothing about where the nucleus is. It's you who say, when you see a whole lot of contours like this, oh, the nucleus must be there. And that's the hypothesis we've been making so far this evening. But is it right? Well, we'd better have a look. How can you find where the nuclei are? Well, here neutron scattering comes in, because neutrons are scattered preferentially by the nuclei. So let's do the same kind of experiment with neutrons and with X-rays and see what we get. Well, there's something about it on this slide. On the left is the result for benzene. Now, I have to admit that this is fudged. No one has given a diagram like this for benzene. What they have given is a diagram for anthracene, in which you've got another ring there and another ring there, so I've just cut those off. I could have brought the anthracene one perfectly well, but it looks rather nicer to compare it with the neutron results on the right. Now, the neutrons here show us some information which the left-hand one doesn't. For example, you'd have to be frightfully clever to say that's where the hydrogen is on benzene. I mean, it might be quite a lot away from there. This isn't a very well resolved peak, is it? So that you would have troubles in getting an accurate position. The hydrogen doesn't have enough electrons. That's the trouble. Here, however, look at this marvelous position for the protons in benzene. You could get a bond length here, CH, extremely well. And what is more important, you can say exactly where the mean position of the nucleus is. And one of the exciting developments in the last year or two has been bringing together of the information that you get from those two types of experiment. Let's look at some calculations which have been made by Dr. Mike Thomas, student who's working with me, now finished and away on his own, which deal with the situation in hydrogen. May we have the last slide? This is a calculation represented by two curves. The dotted curve is the curve of density along the axis, this being the position of the nucleus, the kind of curve which I showed very early on this afternoon. It went up to a very sharp peak. You know, I said that's the mountain peak. Now, when that molecule starts vibrating and the atom moves backwards and forwards, and you ask what happens to the charged cloud, what you find is this solid line. That's what you would have if you could keep the molecule absolutely at rest. But you can't do that. It vibrates, and this is what you get. And the curious thing is that this time the peak comes here. And so when you go down, you find that the position of the nucleus, which you infer from your X-ray work, does not coincide with the position of the nucleus as you would get it from neutron work. So I called it a little light relief, but in fact, if you're really interested in bond length, it could be quite tiresome. It's only really serious for hydrogen atoms, bonds to hydrogen, and there the difference from where you would think it was from an X-ray diagram and where it really is, if you like, got from the neutron diagram, is measurable, and without going into the actual details, the agreement between theory and experiment is quite satisfactory. So there we are, our last tick. Where is the nucleus? Well, you've got to be careful, and particularly if you're dealing with hydrogen, you'd better use some neutrons as well as some X-rays to give you the information that you want. Well, ladies and gentlemen, we've come to the end of the story. It's a rather exciting story, I think, in a way, and it's a story which has only been possible because theory and experiment have flowed together. And you've seen several occasions when I have said, well, now we've got agreement between the results of calculations and the results of measurement. And I think that that is really the sort of thing that you like to have in chemistry, and in other sciences too, because then you really feel that you begin to know what's happening, and I hope that you will feel that you know what happens to an atom in a molecule. Thank you very much.